A very, very warm welcome to this first NoVOC Charge and Connect virtual coffee chat. It's the first one out of 5 so far that we have planned. Virtual coffee chats organized by the NoVOC project. Our idea is to create a virtual platform on the one hand side for knowledge exchange and discussion and for interesting and exciting inputs in the area of sustainable lithium-ion battery manufacturing. I will just quickly show you how this works. So this is really just a 1 hour quick and simple virtual coffee chat. I hope you all have your coffees ready and at hand. They always start the same way. So we'll have a quick welcome and introduction by your respective moderator. We will alternate between NoVOC experts. For today, it's me, Nicole Schmidt, from Utima Research Services. I am the communication manager of the NoVOC project, and together with my colleagues at RISE in Sweden, we have set up this virtual webinar series. So next time you join, you will have another moderator, but for now, it's me. Then we will continue with a quick keynote of 25 minutes. And after the keynote, we will have a 10 minutes breakout session for an informal exchange amongst all of you so that you can connect with your peers and other experts in the field. And after this, we will head into a question and answer session where your respective speaker of the day will answer the questions that we have collected throughout the presentation. And at the very end, we will tease already the next coffee chat that will happen in 2 weeks from now. Just a quick information before I present today's speaker and before we start into the presentation. This webinar will be recorded, but only the part of the presentation. So afterwards, when the question and answer session starts and during the breakout sessions, of course, you're not recorded, so you can speak freely about everything, all your challenges, and ask your questions, whatever it is. I would like to invite you to change your name into first name, last name if you want to, but really first name and institution. You can do so when you hover over your own video in the right upper corner. There is a more button, and then you can rename yourself just so that in case there is a verbal question you have during the question and answer session, I know who to address, and also in the breakout sessions, your other colleagues will know who you are. I would like to invite you also to turn your camera on, of course, especially during the breakout session and the question and answer session. This is supposed to be a very interactive meeting, and also during the presentation, because also for our speaker and me and all of us, it's really nice to see people when talking to the to the black void of the internet. Mute yourself when you're not speaking. And during the presentation, you can already start posting your questions for the question and answer session in the chat. If you prefer to have a verbal question, then I would like to ask you to wait until the question and answer session and then just raise your virtual hand, and I will ask you to take the floor. With this quick info done, let me introduce you to today's speaker. We are very happy and grateful that for our first coffee chat, we have Professor Arno Kwade with us. For most of you, I think I don't really need to introduce him, but nevertheless, a few words on Arno Kwade. He is a professor of mechanical process engineering at the Technical University Braunschweig, and also since 2005, the director of the Institute for Particle Technology, the iPAT, at the Technical University Braunschweig. He's also the chairman of the Battery Lab Factory Braunschweig, the BLB, which is a major interdisciplinary center aiming to scale the entire battery cell value chain from lab to application. And finally, he also serves as the coordinator and chairman of the LiPlanet Network. The LiPlanet Network is the lithium-ion pilot lines network, a Horizon 2020 funded European network bringing together pilot lines for lithium-ion cell production. And as I said, I'm very, very happy and grateful to have Arno with us today, and he will speak about semi-dry and dry production of lithium battery electrodes. So with that, I'm done with the pre-presentation, and I will give the floor to Arno for his input. Have fun, enjoy your coffee, and Arno, floor is yours.
Yeah, thank you very much, Nicole, for the great introduction. And I see that my slide is already
Perfect.
visible, I hope. I was a little bit surprised that it had come so fast, but nice. Okay, so yeah, good afternoon, I have to say. I hope you had a nice lunch, and in the following 25 minutes, I want to tell you something about semi-dry and especially dry production of lithium battery electrodes. This work has been done mainly by my PhDs like Marcilla Nickel, Franziska Beverborg, Svenja Schreiber, or in this semi-dry world, let's say Eike Wiegmann and Finn Reinkensmeyer. And I will also show some results regarding solid-state batteries, which are coming from Finn Frankenberg. I know it's not working forward. I know it's working, yeah. Okay, I just had a little bit, somehow from Zoom it was above my slides a little bit, but now I hope it goes away. So in Braunschweig, as Nicole already said, we have our battery lab factory, which is an interdisciplinary center, and we have 18 PIs, so 18 professors from different disciplines, which are working inside this center. And we are looking on the entire process chain, especially for, we call it circular production of batteries. That means that we start with new material, then we build electrodes and cells out of them. Then we look how they behave during the usage phase and how they age. And then we also have a lot of activities in the recycling of these cells and then taking this material as a secondary material to build new cells. And this we do in the moment in 4 joint research labs. The biggest one is the production lab, so the original BLB. You can see on the left corner here. And we have a few more buildings and facilities, so a diagnosis lab where we can have a look on aged cells, especially. I can build half cells out of them. We have a new education lab, which is not fully finished, but almost. And we have our circular lab, in which we have especially our recycling activities. And today we will also place a first stone, let's say, for a new building where we will have the entire circle again, but then for new battery generations. Now looking on the, let's say, classical route, that means wet processing of the electrodes. We have the electrode production with pre-treatment, mixing especially, then mixing wet, then the coating and drying and the calendering, and all then the assembly of the cells and the finishing of the cells. I think all you know that. And if we now look on the energy demand for the different process steps, you can see that, a lot of energy is required in the coating and drying step. I know that there is also other studies which maybe show 30% of energy, and it's almost, let's say, but it's really the biggest part beside formation and aging. This one can be dropped by maybe have an intelligent usage of the energy during discharging. And the post-drying also depends on how you operate the entire process chain and some energy you need for the dry room. But still, the highest amount goes into coating and drying, and it counts about 30 kilowatt hours for 1 kilowatt hour battery capacity. And the question is, how can we reduce these 40%? And then we are already in our topic. That means that we have to look for dry or semi-dry coating. And by that, we not only decrease the energy demand, we also, let's say, shorten our process chain. So we have a dry powder mixing and formulation, or let's say semi-dry. In a special case, then we have to meter the powder, dose the powder, what is a, let's say, important step, but not really takes a lot of energy or space. And then we have the film formation. and then the lamination maybe on the current collector. And by this relative short process chain, we can also avoid critical solvents. We have a high energy efficiency, as already said. We can lower the CO2 footprint, and also overall we can lower the costs. Even we can, in most cases, increase the performance of the electrodes. And all that shows that it is really valuable to work in the direction of semi-dry and dry coating. But how do the electrode looks like if we change from wet to dry? So first of all, you see here the wet process, typical wet dispersing, and then coating and drying. And you see that we usually have the binder or the carbon binder domain as bridges between the particles, as we already also, for example, simulate that. And we use some NMP or something to dissolve the binder in the solvent. And in the dry coating or semi-dry is similar. We have, let's say, no or only a little bit of solvent, and we have usually binders which have a fibrillation like PTFE, which is in the moment really by far the best binder which we can use. And the binder domain now is a spider web-like carbon binder. And it's more that you put your particles inside this, let's say, spider web, and not that you glue the particles together. So it's, I think, a different adhesive system. Now, coming to my agenda, after the introduction that you just heard, I will come to the dry coating as a main part of my presentation, and then I will have a short look also on semi-dry and also solvent-free all solid state cathode formation before I come to the conclusion. Now, let's start with the dry coating. And the typical dry coating process today looks like it is shown here. You have a mixing process, then sometimes a conditioning process where you, let's say, decrease, for example, the size of the granules which you produce during the mixing. And then you have the dosing by a powder feeding system. And then you have the film formation, in this case here, what is the most typical case, by a calendaring process. We will come to the different processes, mixing, feeding, and film formation later in more detail. In the case of mixing, we can also distinguish between batch mixing, like it is also typical still for wet processing, and continuous mixing, for example, by using extrusion machines. And what we have to do, we have to prevent the breakage of particles, for example, in the mixing step or also during the film formation. We need a really constant and precise mass loading. That means, let's say, a good knowledge about the powder feeding. We have to know what are the steps exactly for the cathode material. We need high process steps, good edges so that we have less scrap, and maybe also a strategy how to handle the scrap afterwards. Coming to the powder mixing process, as I said, continuous or batch. Important at the end is that we have a homogeneous powder with a good fibrillation of the binder. And also the carbon black has to be structured because there is no wet process doing that afterwards. And the granule or agglomerate size has to be adequate for the following film formation step. That means this mixing step at the beginning is really crucial in this case to get a good dry coating. In this presentation, I thought it might be interesting to use a study which we also already published on how the different active material let's say, influence the dry coating process. That is graphite, LFP as a let's say, low-cost cathode material, and NCM as a more high-cost, high-performance active material. And in all formulations, we had some carbon black. So on the anode side, 1.5%, on the cathode side, 3%, and we have almost always 2% of binder PTFE. Here you can see the particle size distribution. So the NCM has the closest and smallest particle size, although the most narrow particle size distribution. And there is then some LFPs. You see it's a polydispersive LFP. There are some primary particles, seems to be. And we have the graphite, which is the widest and coarsest material. Now having a look at our batch mixing process using an Irish mixer usually, then you see that we have a deagglomeration, first of all, of the carbon black at the beginning and also heating up the mixture. Then we're adding the PTFE, and now we are starting to have a fibrillation of the PTFE for 2 minutes and then for 10 minutes, but it's all showing that we take some samples. And at the end, we have the, let's say, finishing and homogenization of the material, which is necessary to have the right granule size for the later film formation. Now, having a look at the results, you see that after first you don't see a, let's say, effect within the particle size distribution, but if you add the granules, which you can see here, but only a small amount of the graphite really agglomerates and forms these granules. And after a longer fibrillation time where the fibers are getting smaller, you see that it's not really a high increase in granules, and for homogenization also most of the graphite is still a primary particle. So it's not such a big interaction of the graphite particles with the PTFE. It looks a little bit different or somewhat different if you look on the cathode materials. So you see here that we have much coarser and much more granules, especially at the beginning of the fibrillation process. So there's a decrease with increasing fibrillation and decrease of fibril size and length. And after homogenization, also we have a decrease in the granulation size and also granulation amount. Looking at the bulk porosity for these different materials, you see that there are quite some differences. After the fibrillation, all have an increase in the bulk porosity, so the volume increases of the overall powder. But there are some differences in the porosity. So the LFP has the highest porosity, the NCM the lowest porosity. And also you see that after 2 minutes, there's no further fibrillation. It seems to be that there's more, let's say, degradation or fibrillation decrease, at least in the length, so that we have more constant or decreasing porosity of the powder. Now coming to the dosing, and I think if you look in the literature and also the patent, which are available, then you see that we have already some pre-metered applications, like it is typical for wet processing. For example, you can choose a needle roller or a vibration chute or a planar sieve, something like that. But what is most common are still self-metered applications using a direct roller infeed, using a calendaring. Also, there are some electrostatic applications which are patented. But what is the by far most common one is using a direct roller infeed in a calendaring machine. So this calendaring machine is really necessary, independent of the dosing methods, to stabilize and form the layer. It can be a simple 2-roll calender if you have a special dosing system, but usually it's a multi-roll calendaring machine where you form the film and also then, let's say, decrease the thickness of the film, and then you have the lamination here at the end on the substrate. The question is how we can get the right film thickness, as the films are too thick due to no slip condition. If we look in the theory, there is a model of Johansen. I wanted to show it you very shortly, that you see that there's already some literature, very old literature from normal roller granulation available. And you see that there's this acceleration zone, then we have the slip zone. Slip zone means that there's still some speed differences between the powder and the roller. And then we come to the nip zone where the powder is really connected to the surface and no slip anymore. That means now the powder is taken into this gap and is compressed, and then you have form the film and get the elastic spring back. But the question here is really the wall friction angle. If the wall friction angle is high, then you have this nip zone very early and you get a lot of material which you have to compress, and then you get automatically a thick electrode, or the torque maybe of the rollers is not sufficient anymore to form the film. So that means low wall friction angles are advantages to get thin films. This we can also see later, but first of all, the question is how we can get thin films. One possibility is to have a multi-step calendering, which is a typical Maxwell process. Then we can have high differential speeds between the rollers, also affecting the film thickness a lot, so that you have the right film thickness already with one, let's say, throughput through the roller gap. And you might be able, to have an exact pre-metering into the gaps, and that might also give you a good film thickness. And if we do that in a more discontinuous way, then you can see it here. So, for example, by increasing or decreasing the line load from the first to the last step, but increasing differential speed of the rollers, you get thinner films. And at the end, it looks really like a, let's say, thick paper, piece of paper, which you can then nicely laminate on the substrate. Now coming to this film formation step, you see that we have normally compaction, normal stresses, but depending on the differential speed of the rollers, also some shearing. And we thought what can be a good measurement techniques. So we have a ring shear cell and we have a uniaxial compression to describe that. And by the ring shear cell, you see that the wall friction angle is the far lowest for the graphite. And that also helps us, to get the right film thickness only after one pass through the calendering gap. But for the other two cathode materials, we need 3 passes to come to the right thickness, and by that areal weight. And what you also can see is that NCM has a, let's say, better flowability. That makes it also even more difficult to come to the good film thickness, because then more powder is flowing into the gap. So that we need more or higher calendering pressures to come down. The porosity is not much changing during the further calendering, but the films are stretched, so they are getting longer and longer, and that is how we get, let's say, thinner films. Looking on the compression, we have a certain test, to have really high compression stresses in the megapascal range. And what you can see is that by this technique, we can come to, let's say, porosities which are very similar to the ones which we get in the later film. So more or less we can forecast what happens in the calendering step if we know the compression stress which is active in the calendering gap. You see that here we have, for example, with the NCM about 40% of porosity, which we also found here for the later film, similar for the graphite, and also the LFP gives us much higher porosity. So this is really nice method, to predict what happens later on in the calendering gap. So this was some results I wanted to show for the dry coating, and I think it's in the moment a really favorable process, and a lot of companies are looking into it and installing the first plants and operating them already. And now I want to come to two more topics very shortly, with really, let's say, less time, which are not installed or not in the industry already. It's a semi-dry coating and it's a solvent-free all solid state cathode production. So the semi-dry coating, it's a new process which we developed at our institute. So we use an extrusion machine, but can also be an, let's say, batch mixer, where we produce with a little small amount of solvent, let's say, wet granules. And these wet granules, which can be shown here, in this case, with a cutting knife, we got the granules, but there are also other possibilities to get wet granules without cutting them. So these are the granules. So they are in the size range of a few millimeters, and then we dose them on a multi-roll calender, in this case 4-roll calender, and form the film similar to the dry coating process. In this case, we have this, let's say, polymer foil to avoid high adhesion to the roller surface, and we have heated rollers, what is also typical for dry coating, what I didn't mention, but we have heated rollers so that we can also have the drying of the electrode only by heating up the electrode by this way. And then we have also a really short process, as we have seen for the dry coating. We have some drying costs, but they are really low compared to the typical normal process. We have short drying times and so on. No further calendering is possible and so forth. And what we found is that the saturation degree of the granules is very important, to get a good result. So we are about 60% of the pores are really saturated, so filled with a liquid. So 40% is air in it, and that gives us a good possibility in the following. And when you compare different extrusion screws, then you can see that by increasing the screw or making it more intensive, you get a higher specific power input to the suspension or to the, let's say, wet powder. Compared to the wet process, which is here on the right side. But at the end, what is seen here, the specific energy requirement is much lower if you have a kneading screw, a little bit higher for the in-test kneading screw, but for the reference, because you need a much longer time, the specific energy put is by far the highest. Depending on the intensity of stresses inside the extrusion machine, we get different microstructures. If we have really high intensities, then we will also break some graphite and get a closer packing. What can be seen here, what is not fully advantageous, you see that the reference is, if we compare the discharge capacities, is the lowest, at least for lower C rates, and we get the best results for the kneading screw, so having a, let's say, moderate dispersing of our particles. It looks a little bit different at higher C rates, where the results come closer together, but still this kneading screw is very advantageous, and we get a better result than for the normal wet process, which is, let's say, also written in the literature, for example, for dry processing. Like we found for dry processing, there's no vibration of binder and very homogeneous pore and material structure. And we can use binders which are, let's say, typical also for wet processing, like CMC and SPR, which are not able to take for full dry processing. Now, last but not least, for maybe 2 or 3 minutes, I want to talk about the solvent-free solid state cathode formation. As you have seen, for the dry processing, that has advantages for the cost and energy demand, but also for especially taking sulfide solid electrolytes. There are no side reactions with the solvent possible. There are no or almost no change in microstructure. There should be no reagglomeration during drying, what might be a problem. And we can also have, let's say, it's easier to have a good atmosphere to avoid a degradation of the solid electrolyte. And we had a nice project where we look of the mixing of these different components, the active material, the solid electrolyte, and the conductive additives, and how we can get a good mixture and then a good microstructure within the cathode. We do it also together with the Yannick group, which are looking more for the electrochemistry and the microstructure, and we for the processing. And one of the recent results, which were just published here in small by Finn Frankenberg, or it will be in a few days, it's at least accepted. We have this process chain, so we have a pre-milled composite, then a fibrillation of the PTFE binder, then we have again the fibrillated mix and the dry film production. And if we look into the results, we see that even if we compare the powder, which is only normal processed or compressed with the electrodes or cathodes we produce by this dry film formation, that we have an increase in performance due to this film formation using the calendering machine. And we are almost getting the reference capacity of our material, forming this dry film for this solid state battery cathode. And this is really, I think, nice to see. And I think dry processes are really the one or the way to go for these sulfide solid electrolytes. So now I want to come to my conclusion. I hope that you have seen that semi-dry coating is able, and dry coating especially, is able to produce high performance lip and also solid state battery electrodes, and that we have really to look on the mixing process. So that is really crucial for the binder fibrillation, for the dispersion of the carbon black, but also later on for the powder flowability, granular size, and so on, which are then important for the film formation during the calendering process. Today, the dry coating is limited to the fibrillated PTFE, so we might find other binders. In the semi-dry coating, we can also use typical binders like CMC or SBR. And there are still some challenges, but I think there's a big progress, and industry is really starting to use this at least dry coating method in a, let's say, standard industrial production of battery electrodes. So we need homogeneous microstructure with a good adhesion also to the electrode film or the electrode current collector. Then constant area life, powder handling, and so on. But I think these are challenges which can be solved really nicely. And finally, I want to thank my PhDs. I already named the most important ones at the beginning, and my postdocs at iPAT. And I want to thank you for your attention. And the last slide I want to at least not leave out is that we're having our conference as every year in November, this time on the 5th and 6th November. And it would be great to see some of you in Braunschweig in about 3 months. Yeah, thank you very much.
Thank you very much, Arno, for your very insightful presentation and also for sharing some current results already from your ongoing projects. I'm very happy that we are also very good in time, so that we will now have the chance to chat and connect in some breakout sessions once again.